So the shortest path algorithms pretty much just try to display the shortest path from the starting city to every other city in the graph. And you see this is the list of that. Like if you said Washington is your starting city, the shortest path distance to Washington itself should be 0. If you want to travel to Atlanta, should be 600. If you want to travel to Dallas, it should be 1300. Now if Washington, you want to travel to Houston, and you want to pass Atlanta, like Washington to Houston, Atlanta, it's going to be 600 plus 800, that's why you have 1400. You may see that this shortest path is already find a shortest path for you. Because if you do another way, you can do Washington to Dallas, Dallas to Austin, and Austin to Houston. The distance is going to be even greater. So that's why it's find the shortest path for you already here. Like another example, Washington travel to Austin. It's going to find the shortest path for you. Saying that go to Dallas first and then go to Austin. Right, and this is 1300 plus 200, that's 1500. As well as Washington to Denver, to Dallas, and then Denver. Right, so that's 2080. And Chicago to Dallas, and then Chicago. You may see that it's not picking Dallas to Denver and Denver to Chicago because that's not the shortest path. So it's actually accumulating and found the shortest distance, which is 1300 plus 900, that's 2200. So this is a single source, right, shortest path algorithms. And you may see the result always find the shortest path for you. So in your assignment, pretty much the same. You have to find all the wedges, right, from your zip code neighbors. Which there are many ways that you can travel. Like it can just say, hey, Washington to Chicago can go through Dallas and Denver and Chicago, which is different zip code, or you can just go to directly like that. But when you run the application, it should show me the shortest path as a result by visiting Washington, Dallas, and Chicago, like that. Washington, Dallas, and Chicago. So you should print out the list of the shortest path to each zip code out, and then from that zip code we can just apply to the final destination by linking between zip code Dallas, Chicago, or the final result is going to be Washington, Dallas, Chicago, 2200 as a distance. Now let's look at the algorithms. So this approach will have some errors, but it's try to show you how we simplify the algorithms here first. So let's take a look. So shortest path, you pass all the graph in that you have constructed, and then you get the start vertex. In this case, we pass Washington as start vertex. Now, start to create the flight method start vertex and start vertex 0. I see. Like this should be start and end, right? Let's see what it is. So we start to NQ the flight. So DQ, go to vertex is not marked. So we start to DQ. So first it's going to be Washington. Get to vertex is not marked. So if it's not marked, then we're going to mark to vertex. We're going to mark Washington. we write flight get from vertex, flight get to vertex. So this pretty much just print like Washington to Washington, and the distance is 0. Right, the first row. And then set from vertex. And get the neighbors. Flight get to vertex, this we get the neighbors. So from Washington, we can get to the neighbors, which is Atlanta and Dallas. And then those are the new from vertex. Now set min distance to flight that get distance. And in Q, vertex Q of vertices adjacent from flight that get from vertex. So we NQ the adjacents, while more vertices in vertex Q get next vertex from vertex Q. And check if vertex not marked, set to vertex. Set the distance. Flight get from vertex. So that's find the weight is, right? To the vertex. So we get the distance. And NQ the flight. As long as it's not empty, keep doing this. Let's see, the algorithms for the charted path traversal is similar to those we use for the depth first and breadth first searches. But there are 3 major differences. PriorityQ rather than first in first out queue. So we can use PriorityQ instead. Stop only when there are no more cities to process. So that means that's the end, no more destination. It is incorrect if we use a reference-based PriorityQ properly. So we see the first one here is kind of there's an error. So we just look at an overview here. Don't focus too much. So now let's focus onto this one, right? We said while more vertices in vertex Q. Get next vertex from vertex Q. If vertex not marked, so we set to vertex and get a distance. So this part of our algorithm walks through the queue of vertices adjacent to the current vertex. We see that keep doing the get right next vertex from vertex Q. So you just try to get adjacents, right? And NQ flights object onto the PriorityQ. The flight variable is actually a reference to a flights object. So you see flight here. Suppose the queue of adjacent vertices has information in it related to the cities Atlanta and Houston. The first time through this loop, we insert information related to Atlanta in flight and NQ it in PQ, PriorityQ. But the next time through the loop, we make changes to the flight object, referenced by flight. We update it to contain information about Houston, and we again NQ it in PQ. So now PQ loses the information it had about Atlanta. So let's look at how to fix this issue. Right, so we can create a new flight from vertex, right? So we get the from vertex, and this is the destination vertex, and we pass it the distance. So let's look at the code from the textbook. Okay.